Good morning, everybody. What I'd like to do over the next half hour or so is just cover some of the development options for the Cortex-A processor from ARM. Cortex has now been around probably about 10-15 years. When ARM released it, they defined 3 profiles that the processor would be available in. Today, probably most of our users are using the Cortex-M profile, which has been built into small microcontrollers for very low power embedded systems. And while this has been hugely successful, the silicon manufacturers have also been creating standard devices based on the Cortex-A profile. So this is a higher performance device, less geared towards real-time, but capable of supporting more feature-rich operating systems such as Linux. In the middle, ARM also defined the Cortex-R profile, which is the real-time profile. This has been less widely used, and it's mainly placed into system-on-chip designs for deeply embedded systems for things like automotive or real-time hard disk drive control. However, we are really starting to see a number of standard devices that provide a mix of processors, either Cortex-A with Cortex-R or Cortex-A with Cortex-M. So these give us interesting devices that can support advanced operating systems, but also perform real-time code with the R or the M processors. So today we're going to have a look at some of the tools that we can use for developing for Cortex-A. While many of you, if you're working with Cortex-M, will be familiar with the Keil MDK-ARM, which is targeted for ARM's Cortex-M processors, ARM also produce a second toolchain called DS5 or Development Studio 5. This is an Eclipse-based toolchain that's designed to support all of ARM's Cortex processors, so that's the A, the R and the M, although it's really geared to developing with the application-specific devices based on Cortex-A. So this provides you a complete toolchain, which is the Eclipse editor, a build system which can either use the GCC compiler or ARM's own compiler, and then it also includes a debugger and a performance analyzer called Streamline as well. So we can code, build and optimize all of our code for an ARM-based processor. One of the big advantages of DS5 is that it's not really a development tool just for Cortex processors. It actually provides a lot of support for specific devices. So again, as we'll see, that you can easily create a debug connection to connect to a standard device and understand all of the peripherals and architecture within that device as well. So it offers you a big head start in developing for a specific manufacturer's device. Within the toolchain, as I mentioned, you can use the GCC compiler, but also included is ARM's own C compiler as well. So this has been under development now really since ARM started as a company, and version 5 of the compiler is a very highly optimized compiler and is also certified for safety critical systems as well. In May this year, ARM will be launching their new version 6 compiler, which is based on a newer code base using LLVM, a low-level virtual machine, and also the Clang system as well. So this will be a new code base which will take the compiler forward to support newer C standards and also achieve higher levels of optimization. So again, you can use this to develop application code, whereas you would need to use the GCC compiler to rebuild Linux. As I mentioned, the other toolchain provided by ARM is really focused on their Cortex-M devices, and this is the Kyle MDK-ARM, and there is a Pro version of this which will also include the new ARM 6 compiler and the safety qualified version 5 compiler. But in May they will also be launching or adding to the Pro toolchain a license to use the DS5 toolchain for specific manufacturers' devices. So this means that if you have the MDK Pro at the minute, you'll be given a license to develop with Cortex-A processors in the near future. So in the initial release, it will be the NXP IMX6 and IMX7 that will be supported, and this may well be extended in the future. So this adds a whole new tool chain for anybody using MDK Pro at the moment. So as I mentioned, DS5 has all of the tools to code and build applications as well as debug and optimize. And what we're going to have a look now is how we can at the debugger that's included in DS5 and also the Streamline optimizer as well. So if you're familiar with Cortex-M, you've been using CoreSight to debug your Cortex-M microcontroller. The same debug architecture is available on Cortex-A devices, however it is considerably more complex. Again, it's capable of supporting a multi-core processor. There are multiple types of trace unit, cross-triggering between different cores, and also a whole bus architecture that's given over to the CoreSight debug architecture. So if you're coming to a Cortex-A device, then the debugger itself is almost a system in its own right. Getting the best out of that does require a good professional tool. So this is really where the DS5 comes in, and it supports a number of different debug adapters. So the high-end performance unit is called DStream. So this allows us to connect and debug any of ARM's current processors, including the new ARM v8 architecture as well. It also has a large trace buffer as well, so we can connect and log all the activity of an external trace unit such as the ETM. For sort of run-of-the-mill day-to-day debugging, we can also use the Kyle U-Link Pro. So this is a lower-cost debug adapter that gives us essentially a run control connection to your debug hardware, and also allows us to connect to and download some of the trace information that's available within these processors as well. Again, as I mentioned, one of the big strengths of DS5 is that it understands all of the, a very wide range of the application-specific devices. So when we come to set up a debug configuration, we can define the debug connection really by selecting the device that we want to use, so in this case a Xilinx Zinc-based device, and then we can define the type of debug connection that we want. So we can do straightforward bare metal debug, we can do Linux application debug, or Linux kernel and device driver debug as well. And selectively we can connect to individual cores within the device, or if we're running a symmetrical operating system such as Linux, then we can connect directly to that and configure and debug on multiple cores. When we're doing Linux application debug, we can connect the debugger to the built-in debug kernel within Linux, the GDB debugger, and also within DS5 we can run multiple debug connections to different cores or application and device driver. So we can debug all the way through our application from the application level into the kernel and into the device driver. We can also select the type of trace that we want to connect to as well. So with dstream, we can connect to the main external trace unit, the ETM, or we can connect to internal trace buffers so that when we halt the code, we can download a snapshot of core activity into the trace window. Once we've established that connection, we have a pretty standard debugger which has all of the features that you'd expect. So here we can see all of the threads that are running on a system, and we've got basic run control of the processor. So we can run, stop, single step, set breakpoints, etc. And we also have a full source code view of our code as well. And that can be extended to tie up to the underlying assembler so that we can see exactly what the processor is doing. We can move from assembler to source window and vice versa. Within our various watch windows, we can also see all of the variables that are within our application. These can be quite extensive, so we can search through and look at these, examine structures, arrays, etc. If we are working with a specific range of variables, we can also put them into a dedicated expressions window, so we can build up a local list of variables that we're actually interested in. So here we can basically highlight a variable and insert it directly into an expression window. And if we want to, we can apply a formula to that variable so we can view it in meaningful units or engineering units as well. We can also look into the CPU. So if we're working at a very low level, we can look at all of the CPU registers and the banked registers for the different operating modes. But also if we're working for device driver work in particular, then DS5 has support for the peripherals that are on devices as well. So we can look into, for example, a CAN peripheral that may be on the device and look down at that at the register level to see exactly how our code has configured it. In terms of breakpoints, we can set software hardware breakpoints, conditional breakpoints which can run scripting files, and the scripting language within DS5 is very Python based, so again it has an extensive and very capable scripting language. We can also set trace breakpoints as well, so we can control trace activity as our code executes. So while we can capture very large amounts of trace data, it's also possible to filter that down so that we capture just the bits of code that we're really interested in, so we can see that very easily in the trace buffer rather than having to go through pages and pages of trace. A lot of the art of using a real-time trace is filtering down to get the information you want rather than capturing vast amounts of data, which just means you're looking for a needle in a haystack. So trace filtering and trace regions are extremely important when you start to work with real-time streaming traces. Within the Cortex-A devices, we also have a memory manager which converts physical to virtual addresses, and this is fully decoded within the DS5 toolchain as well, so we can see exactly how our system is set up and navigate it around it very, very quickly and easily. Again, if you're doing some very basic work with the Linux kernel, then this is extremely useful for you. In terms of the trace buffer, as I mentioned, there are multiple trace units available within Cortex-A devices, and these really work in one of two fundamental ways. We either have an ETM, an embedded trace macro cell, which essentially streams all of the instructions as they're executed out to an external debugger, so we can capture all of the information, all of the instructions that are executed within the processor. or we have an internal trace buffer where it's kind of like a circular snapshot trace, where as the processor runs, we're recording trace activity to an internal memory, so that when we halt the processor, we can download that snapshot trace and then view it within the development tool. Again, the DS5 supports all of the different available trace units within the Cortex processor. So here we have a trace. We can see all of the different thread activity, and this is then decoded into a high-level trace interleaved with assembler code if we want it as well. There's also, within DS5, is a CoreSight library. So once we have our application code developed and we're ready to deploy our product, the CoreSight library can be included, and this can be used to configure the CoreSight debug architecture on our product, so that if in the field we encounter some problems, and we can actually then use this as a sort of a crash debug system, so that you can log all of the trace activity to a file and then basically download this and replay it in the tool. So in the field and sort of early prototyping, you can deploy units. If there are problems, you can collect data from it and see what happened and caused your code to fall over. Also, once we've reached the stage of having a working application, there's also within the DS5 the Streamline performance analyzer that helps us to visualize exactly how our code's running, so that if necessary we can optimize it. So the core of Streamline is a timeline view. So here we have at the top an activity trace that shows the loading on the processor, and this can then be shows then at the bottom here we have all of the thread activity, so we can relate the thread activity to the CPU activity. By clicking on the threads at the side here, we can show either the total aggregate view of all the threads or the individual thread activity, and we can select multiple threads to show their aggregate activity as well. So, and at the top we have a caliper view, which we can change the range of time period that we're interested in looking at our data. So here it gives us a very clear way of seeing, for example, CPU activity and relating that directly back to the thread activity. And again, we can link in any other counters and information that are available in the Cortex performance unit to see exactly how our code is executing on the processor. So in terms of viewing the threads, we have a heat map here. So we can see the color, the darker it gets, shows the more resources it's taking on the processor. But with a button press, we can also move over to show the core activity as well, so we can see in a multi-core system exactly where our code is running at any given moment on which processor. So again, this helps us to visualize our code. When we find an area of interest, we can start to look at the associated source code. So here we have a function view, and this shows us a hierarchy of our functions in terms of the processor resources they're using, so we can easily spot the bottlenecks and important areas of our code, and then we can open up those functions to zoom in and see the critical hotspots within those functions as well. So navigating our code and optimizing it, you're really starting to get a deep amount of information to help you speed up your code. There's also an energy probe as well, so we can actually monitor energy usage against our code as well. So here we're optimizing for performance, but we can do similar things for energy usage as well. And similarly, we can also get a call tree that shows us the impact on the stack and the calling trees within our code as well. Again, so this becomes very easy to visualize. If we want to go and get more information, there's also a method of annotating our code. So we can simply add a file to our code, annotate.h, and this then allows us to add a set of macros to our code, which are basically sending information out of additional trace units within the CoreSight processor, the instrumentation trace. So this then talks to the CoreSight debug architecture and allows us to collect additional information and place that into the performance analyzer so that we can again get more information about how our code's working. So here we're defining some annotation channels, and then we're adding specific annotation points within our code, so that now when we run the Streamline performance analyzer, we're getting information in this case about how our bitmap is being produced, and then in here we're getting additional channels of information that we can zoom in to see the actual activity points and how they're occurring within our code. So you can actually instrument the code and get this displayed graphically, or again there's a text log file that you can save off for analysis in another tool as well. So this allows us to get an even deeper view of exactly what our code is doing as it executes. This is all recorded to a file, so we can go in and analyze it offline, but it's also displayed in real time as the code is running as well. Setting up Streamline is extremely straightforward. We don't have to rebuild the kernel to add an extra driver or anything. We simply need to have an Ethernet connection to our board, and then we can set up the target and basically just install the Gator into the operating system, and then we can select that as the target, and we simply then need to press the go button to start the performance analyzer recording. So at the moment this is done by a driver that's placed within the Linux operating system. In the near future we'll be able also to extend Streamline to do bare metal performance analysis as well. So again, this will use the trace facilities that are within the DS5 debugger. While we've talked about using a feature-rich operating system, the DS5 also supports a wide range of real-time operating systems. So where we have heterogeneous systems which may have a Cortex-A or a Cortex-R and a Cortex-M device, increasingly people are able to run Linux on the Cortex-A, but then a real-time operating system on one of the other cores. So DS5 is capable of creating debug sessions to support debug on both cores, and also is able to debug and understand a wide range of popular RTOSs that are suitable for use on the other processors as well. And in some cases these can actually be used on Cortex-A as well. So we have had some customers who've built Cortex-A based systems using small footprint RTOSs, really just to get very, very high performance systems that they can easily validate. Now, as I say, one of the key RTOSs for working with a Cortex-A device is Linux, and if you are starting to look at using Linux on an embedded systems, one of the key products or key systems to have a look at is Yocto. This is an open source build system specifically aimed at embedded Linux. It allows you to build up a layered system to create a custom distribution for your board. So we can build up a layer which defines the Linux kernel, add another layer which defines your board support package, another layer that defines the applications that you want to add to it as well. Then when we build it, the Yocto system will download all of the packages that we need off the internet and then build our final Linux system. It's absolutely fabulous, and it really does start to work extremely well. But it does really, in addition to building the Linux system, it also has two important considerations if you're building a commercial product. First of all, Yocto places the complete Linux build under your control, so that you can build your system, but at a later date, if an important patch or a vulnerability is discovered in a Linux application, you are able to completely rebuild your system to fix that as soon as patches for those vulnerabilities are put into the Linux mainline kernel. So you're not stuck waiting for a third party, a silicon vendor or somebody else to provide you with a fix to your system. You can do it within hours or days of the vulnerability being discovered. Also within Yocto, you can add your application to the build system as well. So this means that when you do a Yocto build, you can end up with a final image that is a complete production image that you can just hand over to your production site to build the system. So this means going from development to production is a very, very smooth transition, and there's not lots of difficulties getting an easy image to program into your final product. Now we also do a training course for Yocto in the UK. So we do a 2-day course. Next one's in May. The first day gives you a gentle introduction to Yocto, makes it look very easy to use, and then we go deeper into it in the second day and really confuse you. But over the 2 days you get a very good feel for how to use Yocto and how to build it for your system. We're also thinking now of introducing a third day which goes deeper into the Yocto build system, particularly the device tree for ARM-based systems, and this really is the key to building a Linux for custom hardware. So if this would be an interesting course, or a course that you would be interested in, please let me know. Just send us an email and we'll define some dates for that course. And again, my email will be coming up in a little bit. Over the last few years, there have been quite a lot of very low-cost ARM-based hardware, particularly things like Raspberry Pi. But we also provide a number of modules through our partner Phytec in Germany, and these are designed for industrial use and also have guaranteed long-term availability. So basically these modules will be around really until the components are no longer available. And there are a number of these which can be used for prototyping or standard production. So in the middle we have a PHY card which has a standard pinout. So this allows you to design a baseboard and then upgrade the module as more powerful systems become available. The PHY core has the smallest footprint and smallest hardware resources, and it has, for each of the different PHY core modules, it has a different custom pinout. So if you're trying to get the smallest design, lowest cost design, then PHY core, but you are restrained by having to use that module. And then finally, the PHY Flex is a mixture of the two. It has a standard pinout on 2 sockets and then provides an additional pinout which is custom to the specific processor that you're using. All of these come with or available with rapid development kits and increasingly Yocto builds for the Linux operating system to run on these boards as well. In the last couple of years, Phytec have also produced some low-cost baseboards that are customized towards particular types of application, such as industrial control, HMI, or embedded video. and the module plus the baseboard are generally available at a low cost, around 70-80 euros. So again, these are very good development platforms if you have an application that fits one of these baseboards, and they're also suitable for serial production as well. Again, we'll be sending you out a link to download the presentation a little later today, and here are some of the key websites to find additional information. So again, we have a detailed overview of the DS5. You can also download an evaluation toolchain and request an evaluation license as well. It's a very good way to try it out. DS5 also includes a simulator, so it's possible to build a system and run it on either a Cortex-A9 or a Cortex, I think it's an A53 is the second simulator that's included, so you can actually try out an experiment with a Cortex-A processor without any hardware. Phytec will have full range of information about their modules as well, and we will also be taking a deeper look at some of these development systems in a later webinar. We also have a number of training courses that are available via our website. In the near future, next week we have a functional safety seminar, which is on next Tuesday, and I think there are a few places remaining for that. And we regularly run a Cortex-M and RTOS workshop about every other month, and also a full middleware course to look at building complex applications for Cortex-M processors as well. There's also my email on here as well, so if you have any questions, we will answer you at the end of the webinar, or just email me on tmartin@hitex.co.uk. And in Germany, we have a similar set of courses, again a functional safety seminar in April and a middleware course also in April, and in June we have a MDK-ARM power training to take a look at some of the very complex features that are within the MDK-ARM for the Cortex-M processor. I think that takes me through everything that I wanted to cover this morning. Again, if you have any questions or would like further information, please get in touch with us. But thank you for your time this morning,